Today we'll do closed loop transfer function. Okay, transfer function we kind of know. Take any real world example. Anything you are staring at it, starting from a simple resistor capacitor circuit to a monitor screen works, how your eyes work, right? How the ears work. So you could take literally anything that you are right now staring at. A system, engineering system, any system here. Notice when you model it, when you represent it using variables, you typically end up with equations. So this ends up with differential equations. Typically, this ends up with differential equations. Differentials or uh, variants of this. For our level, let's say differential equations. Typically, there is an input here, goes in, an output here. For a differential equation, you have x of t here, and then you have y of t. Okay, and we notice, so the way this y of t would be related to x of t, technically this is, take x of t, this convolution, what is referred to as the impulse response, right? We did this for social media likes, right? So do this operation called convolution, you get it. Convolution is a double integral. Okay, you can technically do it. I mean, it's an integral at the end of the day. Okay, this convolution you can, one integral you could do. Okay, but what happens is, real world you have many systems or many subsystems, many parts to a system. Even if you want to build something like say band pass, right? How we handle the low frequencies, how we handle the high frequencies, how you combine them, right? There are many subsystems involved, right? So you typically have system 1 and then system 2. Then there is a system 3. What happens is, you take the input of what goes in here. That output goes here. Then there is an output here. There is an intermediary output. And parallelly, you also take this to feed it, let's say here. So whenever you have a system like this, right? Simple filter, there is a low pass filter, high pass filter. Low pass filter, you do some, some gain and all that, increase gain, change phase, correct phase, couple of things. And then you combine this with it, let's say. So convolution is extremely inconvenient. In fact, notice the convolution is important component of artificial intelligence. Okay, convolution operation. Computers can kind of handle multiple systems, multiple arrows like this, but typically the way we did it, right? Convolution gets cumbersome. Convolution gets cumbersome unless you are a neural network basically trained for that. This is very, very messy. So what is the way out? This is one important reason you get the Laplace transform. Okay, so notice we start out with a system RC, resistor, capacitor. There is a differential equation corresponding to that. With RC system, there is a first order differential equation. Input and output are related like this. Okay, and you have multiple systems, amount you have multiple systems, convolution gets cumbersome. So what you do is you use use plus transform, where convolution becomes products and things are easy to handle, right? So there is a convolution operator going on here, there is a convolution operator going on here. Now simply things become, there is a product going on here, there is a product going on here. Technically there is also a convolution going on here, and those two gets added up, right? The moment you have two convolutions, two consecutive convolutions, that is when things get messy. It's Laplace transforms, because now things are products. Okay, so with this, what happens is now our system has a transfer function h of s. So what does this transfer function depend on? This could be, simplest example is impedance. Tells you the relation between voltage, say input voltage, and the current across the element. That's the simplest transfer function. So any real life thing correspond to a differential equation. In turn, they could be represented as a transfer function. And here you have this input x of s, you get the output y of s. Life is drastically simplified. Okay, your y of s is just take the original x of s, gets changed by the system transfer function. Okay, okay, let's do two simple examples. Okay, I cannot start from resistor capacitor, but I'm going to start from differential equations. That is, now we'll start with differential equations. Let's quickly see, how this a particular system's transfer function shows up. Okay, so things are a product now, no convolution, just a product, just a product. As I said, so it's a product here, that transfer function gets multiplied here, right? This is very easy to handle. Two convolutions are very hard. Integrals get messy. Two products is fairly easy to handle. This is, let me add, let's say, cascaded convolution. Okay, cascaded convolution gets messy, cumbersome. We use Laplace transform. Okay, so first thing, simplest example. So example, I need transfer function for this. Find transfer function for differential equation. Let's say dy by dt plus t of t equals dx by dt plus 2x of t. Okay, so this is concerning, just find the transfer function. Let me also write down what transfer function is. Transfer function by definition, say t of s, definition is ratio of output to input, t of s by x of s. So in simple words, this is like sensitivity or gain. Sensitivity or gain. Put sensitivity to input or gain function. very colloquial English. Can you find the transfer function for this system? This differential equation? They can give initial conditions, but as far as transfer function is concerned, initial conditions do not matter. If you give initial conditions for transfer function, ignore them. Let's say 0. Okay. For TF, ignore initial condition. F is a transfer function. Ignore initial conditions. So what you have here is y of s plus of s equals s x of s plus 2 x of s. You can pull out the y of s common, you can pull out the x of s common, and you can write so that I got from just took Laplace transform of the differential equation. I got that. And once I have that, this implies this of s into s plus 1 equals x of s into s plus 2. So your y of s by x of s, the transfer function, that is your transfer function, t of s equals s plus 2 by s plus 1. Great. So Shraddha has this, Madhurima has this. So the bottom line is real world resistor capacitors like thing that became equations, differential equations, right? It is giving you transfer function, things are functions of s. So whenever you talk about a transfer function, typically in engineering, there is an underlying system plus this resistor capacitor. Simplest example of transfer function is impedance that we are all used to. Okay. So the simplest, let me also give that example then and there itself. So you have a capacitor. Okay. Notice the equation corresponding to that as V is C is C dV by dt. Okay. And that becomes typically, notice, you could think of ratios between V of s and I of s, voltage by current, V of s by I of s. This should be, how much is this? This is SV here, this is I here. So 1 by SC. So there is a real world element often end up as this transfer functions. Okay. So real world elements, systems, end up transfer function in analysis. talking about something very, very abstract. This just a representation of our engineering problem. Transfer functions. In this case, see this ratio. Let's say we define that as output input. Okay, input is current, output is what is the voltage across the capacitor. Okay, now two quick questions. Now, hey, is this bit clear? See, notice I have a capacitor differential equation, then sort of a transfer function. This is very important to what we are going to look at next. Now we will be only dealing with transfer functions. So this we'll be only talking about this side. Okay, and so this will not be often given no totally abstract. What real world we are talking about, we do not know. In this transfer function, okay, what can we analyze? What can we say? That is the question that we are going to ask. So grounding your understanding in the simple example is very important. Okay, so first important system. So example 2. Example 2. It could be even something like your blood glucose level is the output. What you measure is the output, and what you intend is the input. The stable blood glucose level, homeostatic level, that is the input that you want. Okay, and then what you're measuring current now is the output. So you're going to do some administer drug or something like that, so that you're trying to change your output towards your intended input. Okay, it could be really abstract. Okay, example 2, total net transfer function. We have two systems. One of S, one more system, T2 of S. Input goes here, output goes here. What is the ratio between input and output in the system? We have a cascaded system, that is notice put here, put here is fed as input there, put here. This location, what goes in is the output that comes here. Okay, what comes out here is fed in there. The net transfer function in the system. Put here. So something comes out of that system as fed as input here. So just tell me this. What comes out here? Comes out there. This is after the first system. What should you have there? And everything in terms of yes. What should be here? Got yes here, x here, input through the system. What comes out? x of s, t1 of s. Now that is fed to the second system. Okay, so the output y of s your input goes to the second transfer function. Let's make color code this. This is your input to that system. Input is fed to second system. This is your output. What is the net T of S ratio of input or output for the entire system? You could think of these two as parts, two parts of the system. So if you consider that as a black box, input goes, output comes in. What is the ratio of input to output here? So you got your input to output ratio, y of s by the input x of s happens to be 1 of s, 2 of s. That by definition is the net transfer function T of s. The Isha is looking at input by output. Is always output at the top with respect to input. So technically, this operation is actually very complicated. Even in time domain, that is a convolution. Okay, but very simply, this became a product. So net transfer function is just a product. Net T of s, a cascaded system for cascaded, that is input is fed to the fed as output is fed as input to the other system. That is a cascaded system. Cascaded system is just product. Just product subsystems. This into this. Okay, this was totally new, so I kind of helped you here. Now to do this, let's do. If you have questions, raise it. So again, I'm starting from scratch. So taking anything for granted. Whatever you need to know, I'm trying to show that with a very minimal working example. If you have doubt, raise it before I add another layer of complexity. And notice this system is like now tell you go read, go do practice assignments. Okay, do practice problems, recorded videos, then go take the test. Then you will learn the subject. Right? I go tell you, I just hope that you're going to go do practice and then you're going to take the diagnostic and then you learn. The system is analogous to that. Okay, I'll give you a system that is very different. Okay, so now let's look at example 3. Example 3, transfer function here, net of s here. It's fairly easy. T1 of s, T2 of s, the input goes in parallelly here, parallelly goes there, comes out, and then this is kind of combined here. So you combine, so this is added, comes in here is added. At this junction, this is just a junction, this is a junction, junction. Going on is there summation, things are being summed, and what you get here, this is the output. This is your y of s, what comes is here, and your x of s goes in here. What is a net transfer function? All it says is you are taking x, passing it through system 1, parallelly you are taking x, passing it through system 2. You are adding the two things. You are not cascading, but you are summing. Okay, so what is going on here is summation. Okay, there is a summation going on here. Summation. There is a summation going on here. So this is a junction, and the operation is denoted near the arrow, incoming arrow. Okay, if you look at this, so this is a junction. What you have drawn is a junction. This junction itself is not that important. You have a junction box. Okay, this incoming arrow is added, this incoming arrow is added. This is summation. Given that, what is the net ratio of input to output? This is reasonably easy. So let me help you out with this. So what shows up here is xt1. What shows up here is xt2. By definition, that is a transfer function of that system, right? Output as ratio of input to output. So output as input into transfer function. That is your output. So what is your y of s? And more importantly, what is the net t of s? Can anyone guess? I almost gave it to you. Or y of s. Y of s equals summation of two things. X of s, T1 of s. I am not writing the in Laplace domain. You know, when you put capital letters, this is the Laplace transform variable. You typically put the yes. Okay, so we kind of like, hey, this is in the Laplace domain, so we don't explicitly write it. One of s. Whatever is in the bracket, that is typically not explicitly written. Okay. Anyway, so let me show that at least notation once. You take x, then it goes to t2, right? This x is not explicitly written. This is your net y of s. So your t of s, by definition, this is ratio of input to output, the output to input. That would be placed here. What is it? I'm just taking the two outputs from the systems and adding them. So the transfer function is great. No, Madhurima has it, Niranjana has it. Yeah, that is good. This is simply just T1 plus T2. T1 plus summing, the transfer functions are getting added. Summation remains summation. only cascading convolution changes into a product. Okay, summation is a simple thing. Sum remains a sum. Not surprisingly, not surprisingly, summation remains summation. Summation is a very simple linear operator. Okay. On the other hand, cascading became a product. Cascading is a complicated operator. It became a product. Summation remains a summation. If we pause one after the other, we know what happens. Transfer functions get multiplied. If we pause simultaneously, we know what happens. Things get summed up. So that's your example 3. And I said, so we'll do basics of closed loop transfer function. So this analogy, so I go tell you to read, practice, then take a test, then you learn, right? Things is an open loop. Notice this is again. So good example of open loop is here audio. You're getting audio from this side. You're also getting screen share video from this side. Things are getting summed up, and two different sensors, same input. I am the same person, right? Dr. J. Audio through one device, video through one device, getting added up and it's showing to you, right? So literally anything you see can be modeled and seen in this way, engineering way. Okay. So now the thing is, you could also say you are learning two subjects parallelly. Aptitude while also revising aptitude, and then you are learning a new subject. Say you're learning medical imaging. So two things parallelly happening. Summation also makes sense. Then here also I go tell you, go read, learn, right? Does learning happen? It's a big question, right? So this is also open loop. This is the most important one now. Closed loop transfer function. Now we'll put things in a feedback loop. Notice, for example, I forget to share the screen. You don't see the screen. Now I keep on talking, right? Unless sir, screen share is not working, I get that feedback from you. I'll just continue. And some of you will get after 2-3 minutes, 5 minutes, hey, this is not working, and you will sign off. Learning will happen, right? So this is the open loop system. Extremely unreliable, not robust, and all that. The moment you put feedback, intended in output and what is the actual output, there is a comparison happening. So what goes in here, this is intended output. This is what actually comes out. Then you compare, hey, what is going on here, what I intend and what I actually get. Then we try to design a system such that eventually we get the intended output here. We know the intended output, right? Intended output, we know that. Eventually we get that realized. Okay. So we have to engineer a system, this black box, to get what we want. And for that, what is essential is you put things in a feedback loop. So let's get this. Example 4. Now I'll show the system. I'll give you the transfer function, then I'll show you derivation. Closed loop transfer function. Closed loop transfer function. Okay. Your system is this. What goes in x of s, y of s. This is something that goes through a system. I warmed you up for this abstraction, so I am putting h of s as a system. Okay. So this is roughly intention. What you want, wish. Okay, this is intention or wish. This outcome or reality. Then you provide feedback. Actually measure the outcome, see if things are on, the train is on track. If the plan is going on course, right? If the screen is being shared, it just give feedback. The screen is not shared, give feedback, right? So you give feedback. Or closed loop. Notice we close the loop here. If there is a junction, this input just comes out of it. The task of an engineer is to actually, this is typically the system, this is not in our control. Sometimes this is engineered, but system, this is not really in our control. The task, right, this is a junction box. Often the feedback needs to be sugar coated. Hey, you have no chance of clearing the gate exam, right? Then if I say that, right, that is not serving any purpose. Hey, if this continues, chances of clearing gate exam is very, very bleak, right? So you need to change how you are preparing, how you are learning, how much effort you are putting, right? How dedicated or how diligent you are. You need to change that so that you increase your chances of outcome. Hey, this is not going to cook, right? If you make a blatant statement like that, that's not going to be good. So there is a lot of, this is engineering, but there is a lot of art. Okay, there is an art and craft to this engineering. So I'm going to put, this is kind of crafted. This feedback is crafted, and I'm going to put a system for that. Okay, and in fact, typically this is referred to as G of S, and I'm going to put a H of S here. So this is the feedback is kind of sugar coated or crafted, or this is engineered so that what you intend and what the reality, they match. This bit is engineered. So we are just taking it, no summation and all that. Whatever the value here, take it, feed it in here. And typically the feedback things tend to be unstable if you put positive feedback. How am I doing? Right? I know you're not even giving the diagnostic. Hey, you're doing great, right? Long term, that is not good. You need to give the diagnostic, right? So the feedback, what keeps things stable is you do a negative of what the output is. You do a positive, that is feedback is unstable. Okay, this is intention or wish, and what you really are giving is negative feedback. Does anyone know the closed loop transfer function for this? I'm going to give that to you. If you can recall that, you can solve one control system problem. As in, before I give that, you need to recall that. Does anyone know the closed loop transfer function here? I'll also show the derivation. It's just 2 lines. Does anyone know? Okay, so this is going to be the transfer function here. First, this is the closed loop transfer function CLTF. Okay, closed loop CLTF. And that is, again, by definition, this is y of s by x of s. This is very different from what we have seen so far. This is not a cascade, not a summation, but this is a feedback. Okay, now we have, okay, at least we have two guesses, g by 1 minus gh, and then we have g by 1 plus gh. Yeah, this is going to be, take g, okay, it suffices to recall this. So g by 1, this is as a negative feedback, so this is going to be a plus. Positive feedback, it will be a negative. For negative feedback, it will be a plus. Dot gh. And I didn't write that. Yes. If you want, you can put that yes. Okay. This is even conventionally the yes is not written. You're dealing with transfer function. So this is one thing I recommend you all remember. So I boxed. Notice that yes is sort of a nuisance, no? G by 1 plus gh. That's it. How does this work? You have a summer. This is g. This is your y. Your x goes in. Take whatever comes here, you feed it in here. There is a negative sign. Okay. So what goes in here? We need to know what first. What is this? What is being summed here? So notice what y here. What you have here as yh. Y is fed through the system h. What comes out is yh, because h by definition is ratio of input to output. That is getting subtracted here. So what you get here is x. Then you subtract yh. And finally, what comes out here? Can anyone say that? Goes in as x minus yh. It goes into system G. What comes out? This is simply great. Very good. Okay. This is simply what comes out as g into its input minus yh. Zoom this in a bit so that you could see. Okay, notice you take y, fed it to h, so this is yh that is getting subtracted. So what you have here is x minus yh that goes through g. So what you get is g into input x minus yh. Viola. So g and y are one and the same. G and y are one and the same. Technically, that equals y. Right? There you go. So I'm going to take that. G into x minus yh equals y. That implies gx equals y plus ygh. This implies y by x equals, what is y by x? See, notice the negative there, when it came to RHS, it became a positive thing. And y by h is just, take the y common. This is 1 plus gh. You have a x there, y by x will be what I said initially, g by 1 plus, it's a negative feedback system. This is plus gh. This is what I boxed earlier also. Okay, one last question before we go to PYQs, control system PYQs. We have this. So now, this is example 1, example 2, example 3. We should ask a good question before we proceed further. Let's see who answers this question. So, given in CLTF, closed loop feedback system, given x of s, they have given x of s, they have given g of s, they have given h of s, and h of s. What is this plus p of infinity? We'll put this in a couple of other words, that is, but time tending to infinity. Output is a signal of function of time. What is that output? In fact, this is output. This is not really of interest. So what is r infinity minus y infinity? Okay, that is limit t tending to infinity. What is r of t minus y of t? Or using our notation, you can call this x of infinity minus y of infinity. That is, what is this difference? this difference. What is the difference between input and output after a long time? Let me also write that in English. Okay. That is difference between input and output after a long time. After a long Anyone answer this? What is given as x of s is given, g of s is given, h of s is given. What we want is difference between x of t and y of t. So let me show this to you. So what is I have to draw this once again. Just putting a some reason I put a h there. Given this, they have given this, they have given this. What you want is, so notice there is an x of t here, there is an y of t here. Laplace transformation. Yeah, this is indeed related to steady state. Okay, so this x corresponds to x of t, this y corresponds to a y of t, right? This is y of s, this x of s corresponds to x of t, and then this corresponds to y of t. What we want is the difference between x of t and y of t. This difference. So let's see what we have so far. Y by x is g by 1 plus gh, right? So this is, we want as roughly, so if I do x minus x minus y, right? If I know this, I can Laplace transform, find the, let's say, either function of t, or I can do find something else. So x minus y is essentially x minus y by x, right? So notice this is x into, if I take the x common, 1 minus y by x. So we know this, we know this, we know this. So we know this ratio. So we know this ratio. The input is known. So we technically know the difference between x minus y. What we want is this. The answer is one word. Primo is in the right direction. This has to do with something. This has to do something in the steady state. Okay, and notice t tending to infinity after a long time. That is steady state. Okay, I can correct this. After a long time, that is at steady state. But what we want is the difference between this signal and this signal. Yeah, that is correct. So now Shraddha has this. Now, how do we get that steady state value? How do we get this value? Right now we have x minus y. We can get till that. How do we go from here to there? One word answer. Or one answer is one abbreviation. So let me backtrack. Okay. See what is given us. G is given, H is given, X is also given. Right? So you can technically find Y. So once you find Y, X is given, you can technically find this difference. X of S minus Y of S you can find. Substitute this value in x of y/s. Yeah. Substitute this. So what you have is x of s minus y of s. What we want is x of t minus y of t. We have is this. Yeah, there you go. You use final value theorem. We learned this in the basics of Laplace transform. Apply it here. Final value theorem. You can get this difference. Okay. So we are technically done with the introduction part. I'll show you like one PYQ, solve one PYQ for, I have two PYQs. So each 5 minutes, 10 more minutes, I can show you examples, but notice if we apply final value theorem, we can get that. Okay. So why are we even concerned about this? This is of course at the steady state, but notice X is what we intend or wish. Y is the outcome or reality. So the difference between them is the error. So the difference between these two after a long time is a steady state error. Okay. This has to do with the steady state, and the quantity that I asked specifically is the error. What we are finding here is this is a steady state error. Steady state error. Yes. Okay, and there are a couple of nuances on what the steady state error. There is an actuating error, right? The error is a signal that shows up that we typically call as actuating error. Okay, so there are some subtle nuances, but this is what we intend, what we actually get. That difference is the error, and this specifically is a steady state error. And gate question, if they ask a question in control system, they will ask you what is a steady state error given x, g, and h. One last thing. H of s is 1. This is referred to as unity feedback. You just take the output directly, give it in. No sugar coating and all that. That is referred to as, let's say, unity feedback. Okay, H is 1, it becomes unity feedback. Okay, with that, let's look at two examples and then we'll wind up. Okay, so we are done with the thing. So this is what they ask in gate. Closed loop feedback system given x of s, g of s, x of s. What is a steady state error? What I said, what is x of infinity minus y of infinity? In other words, they ask you the steady state error. Okay, I'll show you two examples, two PYQs. there is no feedback now, I'll just continue without sharing the screen, right? Steady state error is unbounded, it's infinite, right? Laplace transform, basics of transfer. Okay, we have this impulse response. What is the output? This is initial value theorem. Now there is a question on final value theorem. For a non-unity feedback system, G of S is this, H of S is this, magnitude of steady state error. Okay. So for lack of time, I'm going to write, notice E of S is your error. Okay. Then I'm going to write it as X of S minus Y of S. Plus X of S into 1 minus, I'm recalling this formula, G by 1 plus GH. And this is non-unity because of this H. Okay. If nothing is mentioned, you have to presume this is negative feedback by default. You have to presume that. Only positive feedback is explicitly mentioned. This is not mentioned. So this is negative feedback by default. So this is this. And what is your X of S? X of S for unit step input. X is 1 by S. Okay. So that happens to be 1. Now what we want is E of infinity. E of infinity. This is limit tending to 0. E of S. Where do I get this from? This is from final value theorem. Okay. I have the E of S function, Laplace transform. I want to get a particular time value that is at infinity, final value. We got from final value theorem, FVT. That happens to be limit S tending to 0. Yes, E of S is, X of S is 1 by S. Okay. And then we have a bunch of this 1 into 2 by S plus 2 by S plus 2 into 2 by S plus 3. This is S tending to 0 is fairly easy. Okay. Because this into I'm running out of space. So this is 1 plus G is 12 by S plus 2. H is 2 by S plus 3. Note down that formula that we recalled. S is tending to 0. This is fairly easy to handle. First of all, thanks to this got cancelled. S tending to 0, this term is 0, this term is 0, this term is 0. What does this become? 1 minus 12 by 2, that is a 6. 12 by 2, that is a 6. And then 1 plus the 12 by 2 into 2 by 3. How much is this value? At least can you calculate this? What are the 4 options? 0.5, 0.45, 0.25, 0.2. 4 plus 1. So there is a 6 there. 6 into 2 by 3. That will be 1 plus 4, 5. So 6 by 5. 1 minus 6 by 5. Minus 6 by 5. That is minus 1 by 5, right? Minus 1 by 5. And what they want is, I hope, it's a magnitude. The magnitude, so there is no distinction here. What they want is this. So I'll take a magnitude minus 1 by 5. The magnitude of that would be t. You got your 2 marks in control system, basics of transfer function. Okay. Yeah, just be careful with how you handle that. Yes, tending to 0 specifically is convenient, and that s got cancelled. So all the denominators, yes, you can easily, because there is a plus constant, you can neglect the s without issues. How do you solve this? Just tell me how to solve this. Consider a unity feedback system that says as your h of s is 1. Okay, and by default negative feedback, by default negative feedback. Okay, closed loop transfer function is this. So they are given you the closed loop transfer function, right? Notice what they have given you is, by our definition, this is and that g by 1 plus. So this is c is output control system, x is r, and then y is c. Okay, this is just convention. So input is r and then output is c. So c by s, this is technically what we saw so far as g by 1 plus g. This is technically y by x. That by definition is a closed loop transfer function. G by 1 plus g. And they say closed loop transfer function. In fact, they explicitly mention output by input here, just in case you either had a confusion with convention, or you had confusion what is closed loop transfer function, right? This is just the same transfer function we have been talking about. So they gave you this g by 1 plus g. What they want is steady state error now. With respect to unit ramp input, now they put a mild ramp input. What is x of s here? Does anyone know for a ramp what is x of s? For a Dirac 1, step 1 by s. For a ramp, 1 by s square. Okay. Delta goes to 1. U goes to 1 by s. This is step. Okay. T 1 by s square. Notice this also we have seen. Study Laplace transform of t, because t is straight function, right? That is 1 by s square, because often that shows up as a ramp. Okay, now you could go complete the problem. Okay, I have set this up. All they want us, so that is, they want find of infinity where of s is x minus y. Okay, so that equals x into 1 minus y by x. Okay, so e of infinity, this is limit s tending to 0, yes, e of s that equals limit. So if it is infinity steady state, this is s tending to 0, s into x's ramp. So that is 1 by s square. Okay. And then minus, you know, the transfer function y by x is s plus 90. S plus 90. Hope s square plus what? Plus 10s plus 90. Again, tending to 0, fairly easy to find. You could go complete this. Okay. So 1s will cancel. S will cancel. And then tending to 0, 1 by s square, 10s minus s plus 9s plus 90 pi s square plus 10s plus 90. So many of this is tending to 0. Yeah, that is what is surprising. I was wondering, there is this oneness not cancelling. There is a minus 90 there. So that also, that 90 cancels, and now we can cancel this. Now we can find out what the answer is. Okay. So homework, and we'll stop here. Yeah. So this will also cancel. Then, you know, remaining things, all the s terms cancel. This is just 9 by 90. That is 0.1. Okay. So again, if you know the initial value theorem, final value theorem, a good chance of answering the steady state error question in control systems. Okay. You will have to recall one thing. This g by 1 plus gh, that is the ratio of input to output. Error is difference between input and output. Fine. We are slightly over time. Let's stop here. Have a good one. Take care.